What is DevOps and why is it important?
DevOps is a cultural and technical movement that unifies software development, dev, and IT operations, ops, to deliver software faster, more reliably, and with tighter feedback loops. Why it matters? Faster delivery, automated pipelines enable daily or even hourly releases instead of monthly cycles. Higher quality, continuous testing and monitoring catch defects early. Better collaboration, shared ownership eliminates the throw-it-over-the-wall handoff between teams. Reduced risk. Small, incremental changes are easier to troubleshoot and roll back. Business agility. Organizations can respond to market changes and customer feedback quickly. In practice, DevOps combines cultural shifts, blameless postmortems, shared on-call, with technical practices, CI/CD, infrastructure as code, observability, to shorten the SDLC while maintaining reliability.
How does DevOps differ from traditional IT operations?
Team structure. Traditional IT keeps dev and ops in separate silos with distinct goals, features versus stability. DevOps integrates them into cross-functional teams that own the full lifecycle from code to production. Deployment frequency. Traditional shops release every few weeks or months after lengthy change approval processes. DevOps teams deploy daily or multiple times a day using automated pipelines. Automation. Traditional operations rely heavily on manual runbooks and ticket-driven workflows. DevOps automates everything possible: builds, tests, infrastructure provisioning, deployments, and rollbacks. Feedback loops. Traditional teams often learn about problems from end-user complaints. DevOps uses continuous monitoring, alerting, and observability to detect issues in real time. Risk management. Traditional approaches try to reduce risk by deploying less often, which actually increases blast radius. DevOps reduces risk through small, frequent, reversible changes backed by automated testing.
What are the key principles of DevOps?
Collaboration and shared ownership. Dev, Ops, QI, and security work together and share responsibility for the entire software lifecycle, breaking down organizational silos. Automation everywhere. CI/CD pipelines, infrastructure as code, automated testing, and self-service platforms eliminate manual toil and human error. Continuous integration and continuous delivery. Code is merged, built, tested, and made release-ready continuously, not in big batches. Observability and feedback. Monitoring, logging, tracing, and alerting provide real-time insight into system health and user experience, driving data-informed decisions. Security as a first-class citizen, DevSecOps. Security scanning, policy enforcement, and compliance checks are embedded into the pipeline rather than bolted on at the end. Continuous improvement. Blameless postmortems, retrospectives, and chaos engineering drive ongoing learning and system resilience.
Explain the DevOps lifecycle.
The DevOps lifecycle is an iterative loop, often called the infinity loop. With these stages: plan, define features, user stories, and priorities, Jira, Linear, Trello. Code. Developers write and review code in version-controlled repositories, Git, GitHub, GitLab. Build. Source code is compiled and packaged into artifacts, Maven, Gradle, NPM, Docker build. Test. Automated unit, integration, and end-to-end tests validate correctness, JUnit, Selenium, Cypress, Pytest. Release. The validated artifact is promoted through environments and gated for production, GitHub Actions, Jenkins, Argo CD. Deploy. The artifact is rolled out to production infrastructure, Kubernetes, Docker, AWS ECS, Terraform. Operate. The running system is managed, scaled, and maintained, Kubernetes autoscaling, runbooks. Monitor. Metrics, logs, and traces are collected and analyzed to detect issues and inform the next planning cycle, Prometheus, Grafana, ELK Stack, Datadog. The key insight is that monitoring feeds back into planning, creating a continuous loop of improvement.
What are some common DevOps tools?
Source control: Git, GitHub, GitLab, Bitbucket, CI/CD. Jenkins, GitHub Actions, GitLab CI, Circle CI, Argo CD. Configuration management: Ansible, Puppet, Chef, SaltStack. Infrastructure as code: Terraform, Pulumi, AWS CloudFormation, OpenTofu, containerization. Docker, Podman, containered, orchestration. Kubernetes, Docker Swarm, Nomad. Monitoring and metrics: Prometheus, Grafana, Datadog, New Relic. Logging: ELK Stack, Elasticsearch, Logstash, Kibana. Loki, Splunk. Secrets management: HashiCorp Vault, AWS Secrets Manager, SOPs, Artifact Management. JFrog Artifactory, Nexus, GitHub Packages. The right toolchain depends on your stack, team size, and cloud provider. What matters more than specific tools is that they integrate into an automated, observable pipeline.
What is CI/CD, and how does it work?
CI/CD is the backbone of DevOps automation, covering 3 related practices. Continuous integration, CI. Developers merge code to a shared branch frequently, at least daily. Each merge triggers an automated pipeline that builds the code and runs tests. This catches integration bugs early, when they are cheap to fix, rather than during a painful merge day. Continuous delivery, CD. Extends CI by automatically deploying every successful build to a staging environment, making it release-ready at any time. A human still approves the final push to production. Continuous deployment goes one step further by automatically deploying to production without manual approval, relying entirely on automated tests and monitoring to ensure quality. A typical CI/CD pipeline: code push, lint/static analysis, build, unit tests, integration tests, deploy to staging, smoke tests, manual gate or auto, deploy to production. Post-deploy monitoring.
Explain the difference between continuous deployment and continuous delivery.
Both extend continuous integration, but they differ in the last mile. Continuous delivery: every code change is automatically built, tested, and deployed to a staging environment, making it ready for production at any time. However, the actual production release requires a manual approval step. For example, a release manager clicks deploy. This gives teams a human checkpoint for business or compliance reasons. Continuous deployment removes the manual gate entirely. Every change that passes all automated tests is automatically deployed to production. This requires extremely high confidence in your test suite, monitoring, and rollback mechanisms. When to use which. Continuous delivery suits regulated industries, teams building confidence in their pipeline, or when business timing matters, for example, coordinated launches. Continuous deployment suits mature teams with strong test coverage and robust monitoring who want maximum velocity.
What is version control, and why is Git used in DevOps?
Version control is a system that records changes to files over time so you can recall specific versions, collaborate with others, and audit who changed what and why. Why Git dominates DevOps? Distributed architecture: every developer has a full copy of the repository, so work continues even if the central server is down, and operations like branching and merging are fast and local. Branching is cheap. Creating feature branches, experimenting, and merging back is lightweight, enabling parallel development workflows like Git flow or trunk-based development. Ecosystem integration: virtually every CI/CD tool, code review platform, and DevOps workflow is built around Git, GitHub, GitLab, Bitbucket. Auditability: every commit is a permanent, signed record of what changed and why, which is essential for compliance and debugging. GitOps Foundation: Git serves as the single source of truth for both application code and infrastructure definitions, enabling declarative, auditable deployments.
What is infrastructure as code, IIC?
IIC is the practice of managing and provisioning infrastructure through machine-readable definition files rather than manual processes or interactive tools. Key benefits: reproducibility. The same code produces identical environments every time, eliminating works on my machine at the infra level. Version control. Infrastructure changes go through the same code review and Git history as application code. Speed. Spinning up an entire environment takes minutes, not days of ticket-driven manual work. Drift detection. Tools can compare desired state versus actual state and reconcile differences. Two approaches. Declarative. What? You describe the desired end state and the tool figures out how to get there. Terraform, CloudFormation, Pulumi. Imperative. How? You write step-by-step instructions for provisioning, Ansible playbooks, shell scripts. Example tools: Terraform multi-cloud, AWS CloudFormation, AWS specific, Pulumi general-purpose real programming languages, Ansible config management plus light provisioning.
How does a DevOps engineer handle configuration management?
Configuration management ensures that all servers and environments are configured consistently and can be reproduced reliably. How it works in practice: define desired state, write declarative configs, Ansible playbooks, Puppet manifests, chef recipes that describe what packages, files, services, and settings should exist on each machine. Automate enforcement. The CM tool runs periodically or on demand to converge the actual state to the desired state, correcting any drift caused by manual changes. Inventory management. Maintain a dynamic inventory of all hosts, grouped by role, web servers, DB servers, etc. Idempotency. Running the same configuration multiple times produces the same result, making it safe to reapply. Common tools. Ansible agentless uses SSH. YAML-based, easy to learn, great for both config management and orchestration. Puppet agent-based, declarative DSL, strong in large enterprises with complex compliance requirements. Chef agent-based, uses Ruby DSL, popular in organizations with strong Ruby expertise.
What is a container, and how does Docker help DevOps?
A container is a lightweight, standalone, executable package that includes everything needed to run a piece of software: code, runtime, libraries, and system settings. Unlike vmtks, containers share the host OS kernel, making them fast to start, milliseconds, and efficient with resources. How Docker helps DevOps. Consistency across environments. Works on my machine disappears because the container runs identically in development, CI, staging, and production. Fast, reproducible builds. Docker files define the exact build steps, and image layers are cached for speed. Isolation. Each container runs in its own namespace, preventing dependency conflicts between services. Portability. Containers run on any platform that supports the container runtime: Linux, Mac OS, cloud, on-prem. Microservices enabler. Containers are the natural packaging unit for microservices, each running its own process with its own dependencies. Key concepts: Dockerfile build instructions, image immutable template, container running instance, registry image storage like Docker Hub or ECR.
Explain Kubernetes and why it's used in DevOps.
Kubernetes is an open-source container orchestration platform originally designed by Google. It automates the deployment, scaling, and management of containerized applications across clusters of machines. Why DevOps teams rely on it. Automated scheduling. Kubernetes decides which node should run each container based on resource requirements and constraints. Self-healing. If a container crashes, Kubernetes automatically restarts it. If a node dies, workloads are rescheduled to healthy nodes. Horizontal scaling. The horizontal pod autoscaler scales replicas up or down based on CPU, memory, or custom metrics. Declarative configuration. You describe the desired state in YAML manifests, and Kubernetes continuously reconciles the actual state to match. Service discovery and load balancing. Built-in DNS and service abstractions route traffic without manual configuration. Rolling updates and rollbacks. Update deployments gradually with zero downtime and roll back instantly if something goes wrong. Ecosystem, Helm charts, operators, service meshes, and a massive community provide solutions for nearly every operational challenge.
What is a microservices architecture?
Microservices is an architectural style where an application is composed of small, independent services that each handle a specific business capability, communicate over well-defined APIs, typically REST or gRPC, and can be deployed independently. Key characteristics. Single responsibility. Each service does one thing well, for example, user auth, payment processing, notifications. Independent deployment. Teams can update one service without redeploying the entire application. Technology diversity. Each service can use the language, framework, and database best suited to its needs. Fault isolation. A failure in one service doesn't bring down the whole system with proper circuit breaking. Team autonomy. Small teams own entire services end-to-end, enabling faster decision-making. Trade-offs to acknowledge in an interview. Increased operational complexity, networking, distributed tracing, data consistency. Requires mature DevOps practices, CI/CD per service, observability service mesh. Not every application needs microservices. Monoliths are simpler and often the right starting point.
What is a reverse proxy, and why use Nginx in DevOps?
A reverse proxy sits between clients and backend servers, forwarding client requests to the appropriate backend and returning the response. Clients only see the proxy, not the actual servers behind it. Why Nginx is popular in DevOps. Load balancing distributes traffic across multiple backend instances using round-robin, least connections, or IP hash algorithms. SSL/TLS termination handles HTTPS decryption at the proxy layer, offloading that work from application servers. Caching serves static content and cached responses directly, reducing backend load. Security hides backend topology, rate limits requests, and blocks malicious traffic. High performance. Nginx's event-driven, non-blocking architecture handles thousands of concurrent connections with minimal memory. Common DevOps patterns. Nginx as an ingress controller in Kubernetes, as a sidecar proxy, or as an API gateway fronting microservices. Alternatives include HA proxy, Traefik, and Envoy.
How do you monitor system performance in DevOps?
Effective monitoring combines three pillars of observability. Metrics, numerical measurements collected over time, CPU, memory, request latency, error rates. Tools like Prometheus scrape metrics from exporters and applications, and Grafana visualizes them in dashboards. Logs detailed event records from applications and infrastructure. Centralized logging with the ELK stack, Elasticsearch, Logstash, Kibana. Or Grafana Loki allows searching and correlating logs across services. Traces end-to-end request flows across distributed services. Distributed tracing tools like Jaeger or Zipkin show exactly where latency occurs in a microservices call chain. Best practices. Define SL is service-level indicators, and SLOS service-level objectives that tie monitoring to business goals. Set up meaningful alerts that are actionable, not noisy. Alert on symptoms, high error rate. Not causes. Use dashboards for situational awareness, not as the primary alerting mechanism. Implement structured logging JSON for easier parsing and querying.
What is the purpose of logging in DevOps?
Logging captures a chronological record of events in applications and infrastructure. providing the detailed context needed to debug issues, audit activity, and understand system behavior. Key purposes: troubleshooting. When an alert fires, logs provide the why behind the symptom. Stack traces, error messages, request context. Auditing and compliance. Who did what when, from where, required for SOC2, HIPII, PCIDSS. Performance analysis, slow query logs, request timing, garbage collection events. Security forensics, detecting unauthorized access, tracing attack vectors, best practices. Use structured logging JSON format, so logs are machine parsable. Include correlation IDTKS to trace a single request across multiple services. Centralize logs with tools like ELK Stack, Grafana Loki, or Splunk. Never rely on SSHing into individual servers. Set appropriate log levels, DEBUG, INFO, WIRN, ERROR, and avoid logging sensitive data, passwords, tokens, PII.
What are environment variables, and why are they important in DevOps?
Environment variables are key value pairs set outside the application code that configure runtime behavior. They separate configuration from code, following the 12-factor app methodology. Why they matter? Environment portability. The same application image runs in dev, staging, and production with different database URL TKS, IPI endpoints, and feature flags controlled entirely by envvars. Security, sensitive values, IPI keys, DB credentials, tokens. Stay out of source code and Git history. Flexibility, change behavior without rebuilding or redeploying the application. How they're managed in DevOps, locally.
Lenv.
Files never committed to Git. Dynv, in CI/CD, pipeline secrets, GitHub Actions secrets, GitLab CI variables. In Kubernetes, config maps non-sensitive and secrets sensitive. Optionally injected from Vault in cloud. A WS parameter store, Azure App Configuration, GCP Secret Manager.
What is a load balancer, and why is it used?
A load balancer distributes incoming network traffic across multiple backend servers to ensure no single server is overwhelmed, improving availability, reliability, and performance. Types. Layer 4 transport. Routes based on IP and TCP/UDP port. Fast but no content awareness, for example, a WSNLB, HA proxy in TCP mode. Layer 7 application. Routes based on HTTP headers, URLs, cookies, enables path-based routing, SSL termination, and sticky sessions, for example, a WSLB Nginx traffic. Common algorithms. Round-robin requests go to each server in order. Least connections, routes to the server with fewest active connections. IP hash, consistent routing based on client IP, useful for session affinity. Why it matters for DevOps. Enables horizontal scaling, add more servers instead of bigger ones. Provides health checks, automatically removes unhealthy backends from rotation. Enables zero downtime deployments, drain connections from old instances during rolling updates.
What is a service discovery mechanism in microservices?
In a microservices architecture, services are dynamic. Instances scale up/down, move across hosts, and get new IP addresses. Service discovery solves the problem of how does service a fine service be? 2 patterns. Client-side discovery. The client queries a service registry and picks an instance to call, for example, Netflix Eureka plus ribbon. Server-side discovery. The client sends requests to a load balancer/proxy, which queries the registry and routes accordingly, for example, a WSLB, Kubernetes services. Common tools. Kubernetes service discovery, built-in via DNS, service name namespace SVC cluster local, and Kubeproxy. Console, service mesh with health checking, KV store, and DNS/HTTP discovery interfaces. etcd/zookeeper, Distributed KV stores often used as the backend for custom discovery systems. Kubernetes has largely commoditized service discovery for containerized workloads. If you're running on Kubernetes, you typically don't need an additional discovery tool.
How do you implement error handling in a CI/CD pipeline?
A robust CI/CD pipeline anticipates failures at every stage and handles them gracefully. Prevention. Automated testing at multiple levels, unit, integration, E2E, catches bugs before they reach production. Static analysis and linting, catches code quality issues and security vulnerabilities early. Pipeline as code validation, lint your pipeline definitions themselves, for example.
YAMLint, ActionLint,
Detection, exit code handling, fail the pipeline immediately when any step returns a non-zero exit code. Timeout configuration, prevent hung jobs from blocking the pipeline indefinitely. Monitoring and alerting, notify the team on Slack/PagerDuty when builds fail. Recovery. Automatic rollback, if post-deployment health checks fail, automatically redeploy the previous stable version. Retry logic, for flaky external dependencies, package registries, cloud APIs, add idempotent retries with backoff. Manual approval gates, for critical deployments, require human sign-off before proceeding, post-failure. Detailed logs and artifacts, preserve build logs, test reports, and coverage data for debugging, blameless postmortems. Identify systemic issues, not individuals.
Explain the difference between Docker and Kubernetes.
Docker and Kubernetes solve different but complementary problems. Docker is a containerization platform. It packages applications into portable, isolated containers and runs them on a single host. Think of Docker as creating and running individual containers. Builds container images from Docker files, runs containers on a single machine, manages container lifecycle, start, stop, restart. Provides networking and storage for individual containers. Kubernetes is a container orchestration platform. It manages containers across a cluster of machines, handling the operational complexity that arises when you have many containers to coordinate. Schedules containers across multiple nodes in a cluster. Auto-scales based on load, HPI, VPI, cluster autoscaler. Self-heals by restarting failed containers and rescheduling from dead nodes. Manages networking, service discovery, and load balancing across the cluster. Handles rolling updates, rollbacks, and canary deployments. In short, Docker is about creating containers. Kubernetes is about running containers at scale. You typically use both together, Docker, or another runtime like Containered. Builds and runs the containers, while Kubernetes orchestrates them.
What is blue-green deployment?
Blue-green deployment is a release strategy that maintains two identical production environments. Blue, the currently active environment serving live traffic. Green, an idle environment where the new version is deployed and tested. How it works. 1. Deploy the new version to the green environment. 2. Run smoke tests and validation against green. 3. Switch the load balancer/DNS to route traffic from blue to green. 4. Green is now live, blue becomes idle and serves as an instant rollback target. 5. If anything goes wrong, switch traffic back to blue in seconds. Advantages: near zero downtime during deployments, instant rollback, just flip the traffic back. Full production testing before users see the new version. Trade-offs: requires double the infrastructure, though cloud makes this manageable with on-demand resources. Database migrations need careful handling. Both environments must work with the same DB schema during the switch.
How does Terraform differ from Ansible?
While both are IIC tools, they excel in different domains. Terraform. Purpose: infrastructure provisioning, creating and managing cloud resources like VPC-TKS, EC2 instances, RDS databases, S3 buckets. Approach: declarative. You define the desired end state and Terraform plans and applies the changes. State management maintains a state file that tracks all managed resources, enabling drift detection and dependency graphing. Idempotency compares desired state to actual state and only makes necessary changes. Strength, multi-cloud provisioning with a unified workflow. Ansible. Purpose, configuration management and application deployment, installing packages, configuring services, deploying apps. Approach, procedural, tasks run in order. Though modules are individually idempotent, agentless, connects via SSH, no software to install on managed hosts. State stateless, doesn't track what it previously configured. Strength, simple YAML syntax, fast to learn, great for ad hoc tasks and configuration. In practice, many teams use both. Terraform to provision the infrastructure, then Ansible to configure the software on that infrastructure.
What is canary deployment?
Canary deployment is a progressive release strategy where a new version is rolled out to a small subset of users or servers first, then gradually expanded if metrics look healthy. How it works. 1. Deploy the new version alongside the current one. 2. Route a small percentage of traffic, for example, 5%, to the canary. 3. Monitor key metrics, error rate, latency, CPU, business KPIs. 4. If metrics are healthy, gradually increase traffic 5%, 25%, 50%, 100%. 5. If metrics degrade, automatically roll back to the stable version. Advantages over blue-green, lower risk. Issues affect only a small fraction of users. Real production validation with real user traffic can be automated with tools like Flagger, Argo rollouts, or Istio traffic splitting. The name comes from the canary in a coal mine. The canary detects danger before the miners are affected.
What are Helm charts in Kubernetes?
Helm is the package manager for Kubernetes. A Helm chart is a collection of templated Kubernetes manifests that define an application's resources, deployments, services, config maps, etc. Why Helm matters. Templating, parameterize manifests with variables.
Values YAML.
So the same chart deploys to dev, staging, and production with different configurations. Packaging, bundle dozens of Kubernetes manifests into a single versioned, distributable artifact. Dependency management, charts can depend on other charts. For example, your app chart depends on a Redis chart. Release management, Helm tracks releases with versioning, making upgrades and rollbacks simple.
Helm upgrades. Helm rollback.
A ecosystem, Artifact Hub hosts thousands of community charts for common software, PostgreSQL, Redis, Nginx, Prometheus. Example, instead of writing and maintaining 10+ YAML files for a typical microservice, you create one Helm chart with configurable values and deploy it with
Helm install myapp/chart f production values YAML.
What is a rolling update in Kubernetes?
A rolling update is Kubernetes' default deployment strategy that gradually replaces old pods with new ones, ensuring zero downtime. How it works. 1. Kubernetes creates a new pod with the updated version. 2. Once the new pod passes its readiness probe, it starts receiving traffic. 3. An old pod is terminated. 4. This process repeats until all pods are running the new version. Key configuration.
Max surge.
How many extra pods can exist during the update? For example, 25% means you can temporarily have 125% of desired replicas.
Max unavailable.
How many pods can be unavailable during the update? For example, 0 means all old pods must stay running until new ones are ready. Built-in safety. If new pods fail their readiness probes, the rollout pauses automatically. You can then inspect logs and
Kube control rollout undo.
to revert to the previous version.
How do you handle secrets securely in a DevOps pipeline?
Secrets, IPI keys, passwords, certificates, tokens require careful handling at every stage. Storage. Use a dedicated secrets manager, HashiCorp Vault, AWS Secrets Manager, or Azure Key Vault. Never store secrets in Git, even in private repos. Use
Git ignore.
pre-commit hooks and tools like
Git secret.
to prevent accidental commits. Injection. CI/CD pipelines inject secrets as environment variables at runtime, GitHub Actions secrets, GitLab CI variables. In Kubernetes, use secrets objects, base 64 encoded, not encrypted by default. Or integrate with Vault via the Vault Agent Injector or External Secrets Operator, encryption. Encrypt secrets at rest, Vault auto-encrypts. Enable etcd encryption for Kubernetes secrets. Use SOPs or sealed secrets to store encrypted secrets in Git safely. Access control. Apply least privilege. Only the services and people that need a secret should have access. Rotate secrets regularly and automate rotation where possible. Audit access logs to detect unauthorized retrieval.
What is an immutable infrastructure?
Immutable infrastructure is a paradigm where servers and components are never modified after deployment. Instead of patching or updating a running server, you build a brand new image with the changes and replace the old one entirely. How it works. 1. Build a new machine image, IMI, VM image, or container image with all updates baked in. 2. Deploy the new image alongside the old one. 3. Shift traffic to the new instances. 4. Terminate the old instances. Benefits. No configuration drift. Every instance is built from the same image, so there are no snowflake servers. Predictable deployments. If it works in staging, it works in production, same image. Simple rollback, just redeploy the previous image. Security reduces the attack surface since there's no SSH access or manual patching. This is the default model for containers. You never.
Apt-get upgrades.
Inside a running container, you build a new image and redeploy.
What are the different types of Kubernetes services?
Kubernetes services provide stable networking for pods, which have ephemeral IPTKS. Cluster IP default exposes the service on an internal cluster IP, only reachable from within the cluster. Use case, internal microservice to microservice communication. Node port exposes the service on a static port, 30,000 to 32,767, on every node's IP, accessible from outside the cluster via
Node IP, node ports.
use case, development/testing, or when you don't have a cloud load balancer. Load balancer provisions an external cloud load balancer, a WSELB, GCPLB, that routes traffic to the service. Use case, exposing services to the internet in cloud environments. External name maps a service to a DNS name, CNIME record. No proxying, just DNS resolution. Use case, referencing external services, for example, an external database, with a Kubernetes native name. In practice, most production clusters use an ingress controller, Nginx ingress, Traffic, in front of cluster IP services, providing path-based routing, TLS termination, and a single external entry point.
How does Prometheus monitor Kubernetes clusters?
Prometheus is a pull-based monitoring system that scrapes metrics from HTTP endpoints at regular intervals. How it works in Kubernetes. 1. Exporters and instrumentation. Applications expose metrics at
/metrics.
endpoints in Prometheus format. Kubernetes components, kubelet, kubeapiserver, expose metrics natively. For third-party software, exporters, node exporter, kubestate metrics. Translate metrics into Prometheus format. 2. Service discovery. Prometheus uses Kubernetes SD to automatically discover pods, services, and nodes to scrape. Annotations like
Prometheus EO/scrape, true.
control which targets are scraped. 3. Storage. Scraped metrics are stored as time series data in Prometheus Local T SDB, or remote storage like Thanos/Cortex for long-term retention and high availability. 4. Querying. PromQL allows powerful queries like
rate HTTP request total status equals 505 M.
to compute error rates, percentiles, and aggregations. 5. Alerting. Alert Manager evaluates alert rules and routes notifications to Slack, PagerDuty, email, etc., with grouping, silencing, and inhibition to reduce noise. Common setup. The Prometheus Stack Helm chart deploys Prometheus, Alert Manager, Grafana, and standard dashboards in one step.
What is the difference between monolithic and microservices architectures?
Monolithic architecture. The entire application is built, deployed, and scaled as a single unit. All modules, UI, business logic, data access, share the same codebase and process. Microservices architecture. The application is decomposed into small, independent services, each owning its own data and business logic, communicating via APIs. Key differences. Scalability. Monoliths scale vertically, bigger server, or by replicating the entire app. Microservices scale individual services independently based on demand. Deployment. A change to any part of a monolith requires redeploying the whole application. Microservices allow independent deployment of individual services. Development speed. Monoliths are faster to develop initially. Microservices shine as teams and codebases grow, enabling parallel development by autonomous teams. Complexity. Monoliths have simpler operational overhead, one thing to deploy and monitor. Microservices introduce distributed systems complexity, networking, consistency, observability. Interview insight. Many successful companies start monolithic and migrate to microservices as they scale. Premature decomposition into microservices is a common anti-pattern.
How does Ansible differ from Chef and Puppet?
All three are configuration management tools, but they differ significantly. Ansible, agentless, connects to hosts via SSH or WinRM for Windows. Nothing to install on managed nodes. YAML-based playbooks are easy to read and write, even for non-developers. Push-based. You run playbooks from a control node when needed, or on a schedule via IWX/Tower. Procedural. Tasks execute in order, though individual modules are idempotent. Learning curve, lowest of the three. Productive within hours. Puppet. Agent-based. Requires a Puppet agent on every managed node that periodically pulls config from a Puppet server. Declarative. DSL. You describe the desired state, and Puppet figures out how to achieve it. Strong in enterprises. Mature, with extensive compliance and reporting features. Learning curve. Moderate. Custom DSL takes time to learn. Chef. Agent-based. Chef client runs on each node, pulling from a Chef server. Ruby DSL. Recipes and cookbooks are written in Ruby, offering great flexibility but higher complexity. Learning curve. Steepest. Requires Ruby knowledge. Current trend. Ansible dominates for most use cases due to its simplicity and agentless architecture. Containerized environments have also reduced the need for traditional CM tools.
How do you ensure high availability in a cloud environment?
High availability, HI, means designing systems to remain operational even when components fail. Infrastructure level. Multi-IZ deployments. Distribute instances across multiple availability zones so a single IZ failure doesn't take down the service. Multi-region. For critical services, replicate across geographic regions for disaster recovery. Load balancing. Distribute traffic across healthy instances and automatically remove unhealthy ones. Application level. Auto-scaling. Automatically add/remove instances based on demand. A WSISG, Kubernetes HPI. Stateless design. Store session state externally. Redis, DynamoDB. So any instance can serve any request. Circuit breakers. Prevent cascading failures when downstream services are unhealthy. Data level. Database replication, read replicas, multi-IZRDS, or distributed databases, Cockroach DB, Aurora. Automated backups, regular snapshots with tested restore procedures. Caching, reduce database load with Redis/memcached. Operational. Health checks, deep health checks that verify the service can actually do work, not just that the process is running. Chaos engineering, regularly test failure scenarios to validate your HI design.
How do you handle stateful applications in Kubernetes?
Stateful apps, databases, message queues, caches need special handling because they require stable identities, persistent storage, and ordered operations, things that stateless deployments don't need. Kubernetes primitives for stateful workloads. Stateful sets provide stable, unique network identities, pod 0, pod 1, ordered startup/shutdown, and stable, persistent storage per pod. Essential for clustered databases like PostgreSQL, MySQL, or Kafka. Persistent volumes, PV, and persistent volume claims, PVC, decouple storage from pod lifecycle. When a pod restarts, it reattaches to its existing volume with all data intact. Storage classes define different tiers of storage, SSD versus HDD, replicated versus local, and enable dynamic provisioning of volumes. Headless services provide DNS records for each individual pod, pod 0, service name, instead of a single cluster IP, enabling direct pod-to-pod communication needed for database clustering. Best practice: consider using Kubernetes operators, for example, Cloud Native PG for PostgreSQL, Strimzi for Kafka, that encode operational knowledge for specific stateful applications, handling backups, failover, and scaling automatically.
What is a sidecar container pattern in Kubernetes?
The sidecar pattern runs a helper container alongside the main application container within the same pod. Both containers share the pod's network namespace, localhost, and can share volumes. Common use cases: logging agent. A Fluent or FileBeat sidecar tails application log files and ships them to a centralized logging system, so the app doesn't need a logging SDK. Service Mesh Proxy, Envoy sidecar, injected by Istio or Linkerd. Handles mutual TLS, traffic management, and observability transparently. Secret injection, Vault agent sidecar fetches and refreshes secrets, writing them to a shared volume the app reads from. Monitoring, a Prometheus exporter sidecar, exposes application-specific metrics. TLS/auth proxy, a sidecar handles authentication and TLS termination, so the app only deals with plain HTTP. Why sidecars work well. Separation of concerns, the app focuses on business logic. Reusable, the same sidecar image works with any application. Independent lifecycle. Update the sidecar without changing the app.
How do you implement security in a CI/CD pipeline?
Security must be embedded at every stage of the pipeline, not bolted on at the end. Code phase. SIST, static application security testing. Scan source code for vulnerabilities, Sonar Quebec, Semgrep Code QL. Secret scanning, detect accidentally committed credentials. Git secrets, Trufflehog, GitHub secret scanning. Dependency scanning, check for known vulnerabilities in third-party libraries. Dependabot, Snike, OWASP dependency check. Build phase. Container image scanning, scan images for CVEs before pushing to registry, Trivy, Gripe, Claire. Minimal base images, use Distroless or Alpine to reduce attack surface. Image signing, sign images with cosign/notary to ensure provenance. Deploy phase. Policy enforcement, use OPA/gatekeeper or Kyverno to block non-compliant deployments. For example, no running as root no.
Layerist.
Tags, RBAC, limit who and what can deploy to each environment. Network policies, restrict pod-to-pod communication to only what's needed. runtime. DIST, dynamic application security testing. Test the running application for vulnerabilities, OWASP ZIP. Runtime protection, monitor for anomalous behavior, Falco SysTig.
What is the concept of shift left in DevOps security?
Shift left means moving security testing and practices earlier to the left in the development lifecycle, rather than treating security as a final gate before production. Traditional approach shifted right, code, build, test, security review, deploy. Vulnerabilities are found late when they're expensive to fix. Shift left approach. Security, code, build, test, deploy. Security is integrated from the start. What shift left looks like in practice. IDE plugins, developers get security feedback as they write code. Snike IDE, Sonar lint. Pre-commit hooks, block commits that contain secrets or fail linting rules. PR level scanning. SIST and dependency scanning run on every pull request, with findings shown as PR comments. Threat modeling, security architects participate in design reviews, not just code reviews. Security training, developers learn secure coding practices, not just security engineers. Why it matters. Fixing a vulnerability in development costs 6 to 10x less than fixing it in production. Shift left catches issues early, reduces risk, and avoids the bottleneck of a security team reviewing everything at the end.
What is a Kubernetes daemon set?
A daemon set ensures that a specific pod runs on every node or a subset of nodes in the cluster. When new nodes join, the daemon set automatically schedules the pod on them. When nodes are removed, those pods are garbage collected. Common use cases: log collection, run Fluent or FileBeat on every node to collect and forward container/system logs. Node monitoring, run Node Exporter on every node to expose hardware and OS metrics to Prometheus. Networking, CNI plugins, Calico, Cilium, and QProxy run as daemon sets. Storage, CSI drivers that need to run on every node for volume mounting. Security, agents like Falco for runtime security monitoring on every node. Node targeting, you can restrict a daemon set to specific nodes using
Node selector.
or
Affinity.
rules. For example, only run a GPU monitoring agent on GPU nodes.
What is the difference between proactive and reactive monitoring?
Proactive monitoring anticipates and prevents issues before users are affected. Set threshold-based alerts, for example, alert when disk usage exceeds 80% before it hits 100%. Monitor trends and anomalies, for example, error rate increasing over the last hour, even if still below the SLO. Capacity planning, track resource usage trends to scale before you run out. Synthetic monitoring, simulate user journeys, health checks, uptime pings, to detect failures before real users do. Chaos engineering, deliberately inject failures to find weaknesses proactively. Reactive monitoring, detects and responds to issues that have already occurred. Alert on symptoms, for example, 5xx error rate exceeds SLO, latency spikes. Log analysis after an incident to determine root cause. On-call response to pages and customer-reported issues. Post-mortem analysis to prevent recurrence. A mature monitoring strategy is mostly proactive. You should be detecting and fixing issues before users notice them. Reactive monitoring is the safety net for what proactive monitoring misses.
What is the role of service mesh in Kubernetes?
A service mesh is a dedicated infrastructure layer that handles service-to-service communication, extracting networking concerns out of application code and into the platform. What it does: traffic management, canary deployments, traffic splitting, retries, timeouts, and circuit breaking configured declaratively, not coded into each service. Security, automatic mutual TLS, between all services, encrypting all inter-service traffic without application changes. Observability, collects detailed metrics, traces, and logs for every request between services, giving you a complete picture of service communication. Policy enforcement: define and enforce access control policies, which services can talk to which. How it works: a sidecar proxy, typically Envoy, is injected into every pod. All traffic in and out of the pod flows through this proxy, which enforces the mesh's policies. Popular implementations: Istio feature-rich, most widely adopted, steeper learning curve, Linkerd, lightweight, simpler, lower resource overhead. Cilium Service Mesh, eBPF-based, no sidecars needed, high performance.
How do you secure a Kubernetes cluster?
Kubernetes security requires defense in depth across multiple layers. Authentication and authorization: enable RBAC and follow least privilege. Don't use clusteradmin for everything. Integrate with identity providers, OIDC. For human access, use service accounts with scoped permissions for workloads. Disable anonymous authentication and the default service account token auto-mount. Network security: apply network policies to restrict pod-to-pod traffic, default deny, then whitelist. Use a service mesh for mutual TLS encryption between services. Restrict IP iServer access to trusted networks, workload security. Enforce pod security standards, restricted profile. No root containers, no privileged mode, read-only root file system. Scan container images for CVEs before deployment, Triv, gripe. Use admission controllers, OP/gatekeeper, Kyverno, to enforce policies at deploy time, secrets. Enable etcd encryption at rest. Use external secrets managers, Vault, AWS secrets manager. Instead of plain Kubernetes secrets, rotate secrets regularly, runtime. Monitor with Falco for anomalous system calls. Enable audit logging on the IP iServer. Keep Kubernetes and Node OS patched and up to date.
How would you handle a production failure in a CI/CD pipeline?
A structured incident response for a deployment-related production failure. 1. Detect automated monitoring and alerting, Prometheus/Grafana PagerDuty, surfaces the issue. Key signals: error rate spike, latency increase, health check failures, customer reports. 2. Triage determines severity and scope. Is it a partial degradation or full outage? Which services are affected? Did a recent deployment cause it? Check.
Kube control rollout history.
And deployment timestamps. 3. Mitigate, restore service first, investigate root cause later, if caused by a recent deployment.
Kube control rollout undo.
Or trigger the previous pipeline version, if infrastructure related. Scale up healthy instances, failover to backup region, communicate status to stakeholders. 4. Investigate, once the immediate impact is resolved. Correlate logs, metrics, and traces around the failure timestamp. Review the code diff in the failing deployment. Check for external factors, dependency outage, cloud provider issue. 5. Fix and verify, write and test the fix. Deploy through the full pipeline, don't hotfix production directly. 6. Post-mortem, conduct a blameless review documenting what happened, timeline, root cause, impact, what went well, and action items to prevent recurrence. Share findings with the broader team.
What is GitOps and how does it work?
GitOps is an operational framework where Git is the single source of truth for both application code and infrastructure/deployment configuration. Changes to the system are made by updating Git, and automated tooling ensures the live environment matches what's in Git. Core principles. Declarative: the entire desired state of the system is described declaratively in Git, Kubernetes manifests, Helm charts, customize. Versioned and immutable: every change is a Git commit with full audit trail, authorship, and the ability to revert. Pulled automatically: an agent running in the cluster continuously compares the live state to the Git state and reconciles any differences. Continuously reconciled, drift is automatically corrected, even manual.
Kube control.
Changes are overwritten to match Git, common tools. Argo CD, declarative Git, ops CD for Kubernetes with a powerful UI and multi-cluster support. Flux, lightweight, CNCF graduated Git ops toolkit that integrates with Helm, Customize, and OCI registries. Benefits, faster deployments, merge a PR equals deploy, easy rollbacks, revert a commit. Strong audit trail and reduced access to production, developers push to Git, not to clusters.
How do you monitor microservices?
Monitoring microservices is harder than monoliths because a single user request may traverse dozens of services. You need all three pillars of observability. Distributed tracing traces a single request as it flows through multiple services, showing latency at each hop. Tools: Jaeger, Zipkin, a WS X-ray, Grafana Tempo. Requires instrumentation. Open telemetry is the standard. To propagate trace context, centralized logging, aggregate logs from all services into a single searchable platform. Include correlation ID to KES so you can filter all logs for a single request across services. Tools: ELK Stack, Grafana Loki, Splunk, metrics. Collect RED metrics per service, rate, request/sec, errors, error count/rate, duration, latency percentiles. Use USE metrics for infrastructure. Utilization, saturation, errors, tools, Prometheus plus Grafana, Datadog, additional practices. Service level objectives, SLOS. Define reliability targets per service, for example, 99.9% of requests under 200 ms. Dependency mapping, visualize service dependencies to understand blast radius. Alerting on SLO burn rate. Alert when you're consuming your error budget too fast, not on arbitrary thresholds.
How does service mesh improve microservices security?
A service mesh dramatically improves microservices security by making it automatic and application transparent. Mutual TLS encrypts all service-to-service traffic automatically. No code changes needed. Both sides authenticate each other using certificates managed by the mesh, auto-rotation, no manual cert management. Prevents eavesdropping, man-in-the-middle attacks, and spoofing within the cluster. Authorization policies define fine-grained access control. Service a can call service BTKS.
/API/orders.
Endpoint with GET, but service C cannot. Policies are enforced at the proxy level, independent of application code, deny by default posture, only explicitly allowed traffic flows. Traffic observability, full visibility into who is calling whom, with what frequency, and what success rates. Anomaly detection, spot unusual traffic patterns that may indicate compromise. Rate limiting and circuit breaking, protect services from abuse or cascading failures, limit request rates per source service. Example: with Istio, you deploy a
Peer authentication.
policy for mutual TLS and an
Authorization policy.
for access control, zero application code changes required.
What is Open Policy Agent, OPA?
OPA is a general-purpose, open-source policy engine that decouples policy decisions from application logic. You write policies in OPA's declarative language, REGO. And OPA evaluates them against input data to produce allow/deny decisions. How it works in DevOps. Kubernetes admission control, via OPA gatekeeper, enforce policies on every resource created in the cluster. For example, all images must come from our private registry. No pods can run as root. Resource limits are required. CI/CD pipeline gates. Validate Terraform plans, Kubernetes manifests, or Docker files against policy before deployment. IPI authorization, microservices query OP, for fine-grained access decisions. Can user X perform action Y on resource Z? Infrastructure compliance, ensure cloud resources meet organizational standards. tags required, encryption enabled. Why OPA matters? It provides a unified policy framework across the entire stack. Instead of implementing ad hoc validation logic in every tool and application, you write policies once in Rego and enforce them everywhere.
How do you manage secrets in Kubernetes?
Kubernetes offers built-in secrets, but production environments need additional safeguards. Kubernetes secrets built-in. Store sensitive data as base 64 encoded values, not encrypted by default. Mounted as files or environment variables in pods. Require enabling etcd encryption at rest to actually be encrypted in storage. Limited access control via RBAC, external secrets managers, recommended for production. HashiCorp Vault, full-featured secrets management with dynamic secrets, auto-rotation, audit logging, and fine-grained ICLTKS. AWS Secrets Manager / GCP Secret Manager / Azure Key Vault. Cloud-native options with tight IAM integration. External Secrets Operator. Sync secrets from external managers into Kubernetes secrets automatically. Best practices. Never hardcode secrets in manifests or Docker files. Use sealed secrets or SOPs if you must store encrypted secrets in Git. Rotate secrets regularly and support rotation without pod restarts. Vault agent, projected volumes. Audit who accesses secrets and when. Use short-lived, dynamically generated credentials where possible. Vault dynamic secrets for databases.
How do you optimize Kubernetes performance?
Kubernetes performance optimization spans compute, networking, and scheduling. Right-sizing workloads. Set resource requests what the pod needs, and limits maximum allowed, based on actual usage, not guesses. Use vertical pod autoscaler, VPI, to get right-sizing recommendations automatically, avoid over-provisioning, wasted cost. And under-provisioning, OOM kills, throttling. Scaling, horizontal pod autoscaler, HPI. Scale replicas based on CPU, memory, or custom metrics, request rate, queue depth. Cluster autoscaler, add/remove nodes based on pending pod demands. KEDI, event-driven autoscaling for queue-based or cron-based workloads. Networking. Use efficient CNI plugins, Cilium with eBPF for high throughput. Enable topology-aware routing to keep traffic within the same IZ. Tune connection pooling and keep alive settings, scheduling. Use pod topology spread constraints to distribute workloads evenly across nodes and zones. Use pod affinity / anti-affinity to co-locate or separate related workloads. Use priority classes to ensure critical workloads get scheduled first during resource contention. Monitoring. Continuously profile resource usage with tools like Kubecost, Prometheus, and Grafana to identify waste and bottlenecks.
How do you ensure compliance in DevOps pipelines?
Compliance in DevOps means automating governance so it doesn't slow down delivery. Policy as code. Use OP/gatekeeper or Kyverno to enforce policies as Kubernetes admission controllers. For example, required labels, image source restrictions, resource limits. Validate Terraform plans and Kubernetes manifests against policy in CI before they ever reach a cluster. Audit logging. Enable Kubernetes IP server audit logging to capture who did what and when. Centralize audit logs from all systems, cloud provider, CI/CD, application, for correlation. Use immutable log storage to prevent tampering, access control. Implement RBAC with least privilege across all systems, Kubernetes, cloud accounts, CI/CD, Git repos. Use SSO and MFI for all human access. Regularly review and prune access permissions, supply chain security. Sign container images, cosign, and verify signatures before deployment. Generate and verify SBOMs, software bill of materials. For every release, pin dependencies and use lock files to prevent supply chain attacks. Continuous compliance. Run compliance checks in CI, CIS benchmarks, SOC2 controls. Treat violations as build failures. Automate evidence collection for auditors rather than scrambling during audit season.
What is chaos engineering, and why is it used?
Chaos engineering is the discipline of experimenting on a system to build confidence in its ability to withstand turbulent conditions in production. Core idea: rather than waiting for failures to happen and hoping your systems handle them, you deliberately inject failures in a controlled way to discover weaknesses before they cause real outages. How it works: 1. Define steady state. Identify measurable indicators of normal system behavior, latency, error rate, throughput. 2. Hypothesize. If we kill 30% of the pods, the system should auto-heal within 60 seconds with no user impact. 3. Inject failure. Introduce the disruption, pod kill, network latency, CPU stress, IZ outage simulation. 4. Observe, monitor whether the system maintains steady state or degrades. 5. Learn if the hypothesis fails, you found a weakness to fix before it causes a real incident. Common tools: Chaos Monkey, Netflix. Randomly terminates instances. Litmus Chaos, Kubernetes native chaos experiments. Gremlin, Enterprise Chaos Engineering Platform. Chaos Mesh, CNCF project for Kubernetes fault injection. Key principle: start small, kill one pod in staging, and gradually increase scope and blast radius as confidence grows. Always have a way to stop the experiment immediately.
How do you implement zero downtime deployments?
Zero downtime deployment means updating your application without any interruption to user traffic. Several strategies achieve this: rolling updates, Kubernetes default. Gradually replace old pods with new ones, configure.
Max unavailable, 0.
To ensure old pods stay until new ones are ready, requires proper readiness probes to prevent routing traffic to unready pods. Blue-green deployments. Run 2 full environments. Switch traffic atomically at the load balancer. Instant rollback by switching back. Higher infrastructure cost during the transition. Canary deployments. Route a small percentage of traffic to the new version first. Gradually increase if metrics are healthy. Tools: Argo rollouts, Flagger, Istio traffic splitting. Critical requirements for all strategies: health and readiness probes. Kubernetes must know when a pod is truly ready to serve traffic. Graceful shutdown, handle SIGTERM, finish in-flight requests before terminating, pre-stop hooks.
Termination grace period seconds.
Backward compatible changes. The new version must work alongside the old version during the transition, especially important for database schema changes and IPI contracts. Connection draining. Load balancers must stop sending new traffic to pods being terminated while allowing existing requests to complete.
What are the best practices for managing multi-cloud infrastructure?
Multi-cloud, using AWS plus GCP plus Azure, etc., adds complexity but provides vendor independence and resilience. Infrastructure as code. Use a cloud-agnostic IIC tool like Terraform or Pulumi to manage resources across providers with a unified workflow. Abstract provider-specific details into reusable modules while accepting that some resources are inherently provider-specific. Networking. Establish secure cross-cloud connectivity, VPN, dedicated interconnects. Use consistent CIDR planning to avoid address conflicts. Consider a service mesh that spans clouds for unified service communication, security, and identity. Centralize identity management, Okta, Azure ID. With SSO across all cloud consoles and tools, standardize IAM policies and naming conventions across providers. Use a unified secrets management solution. Vault works across clouds. Observability. Use a single monitoring platform, Datadog, Grafana Cloud, that aggregates metrics, logs, and traces from all clouds. Standardize on open telemetry for instrumentation to avoid vendor lock-in. Cost management. Use FinOps practices with tools that provide cross-cloud cost visibility, cloud health, Kubecost. Tag resources consistently across all providers for accurate cost allocation.
How do you secure container images?
Container image security is critical because a compromised image affects every environment it runs in. Build time. Use minimal base images. Alpine, distroless, or Scratch images have fewer packages and therefore fewer potential vulnerabilities. Multi-stage builds, separate build dependencies from runtime. The final image only contains what's needed to run, pin versions, use specific image tags and digest hashes, never.
Layerist.
To ensure reproducible builds, don't run as root set.
USER non-root.
In the Docker file, use read-only file system where possible, scanning. Scan in CI, run Trivy, Gripe, or Snike on every image before it's pushed to the registry. Scan in registry. Enable automatic scanning in your container registry, ECR, GCR Harbor. Block deployments. Use admission controllers to reject images with critical/high CVEs. Supply chain. Sign images. Use cosign to cryptographically sign images and verify signatures before deployment. Use trusted registries. Only allow images from your private registry, not public Docker Hub. Generate SBOMs. Track all components in your images for vulnerability tracking and compliance. Runtime. Monitor running containers for anomalous behavior, Falco. Enforce read-only root file systems and drop unnecessary Linux capabilities.
How do you manage Kubernetes upgrades with zero downtime?
Upgrading a Kubernetes cluster, control plane plus nodes, requires careful planning to avoid disrupting workloads. Control plane upgrade. Upgrade one minor version at a time, for example, 1.28, 1.29, not 1.28, 1.30. Manage services, EKS, GKE, IKS. Handle control plane upgrades with minimal disruption. Self-managed clusters. Upgrade one control plane node at a time in an HI setup. Node upgrade the critical part. 1. Cordon the node.
Kube control cordon node.
Marks it unschedulable so no new pods land on it. 2. Drain the node.
Kube control drain node. Ignore daemon sets. Delete empty your data.
Gracefully evicts all pods, respecting pod disruption budgets. 3. Upgrade the node, update kubelet, container runtime, and OS packages, or replace with a new node image. 4. Uncordon.
Kube control uncordon node.
Marks it schedulable again. 5. Repeat for each node, key safeguards, pod disruption budgets, PDBs. Ensure a minimum number of replicas stay available during the drain. Surge nodes, add extra nodes before draining old ones, so there's always capacity for evicted pods. Test in staging first. Run the full upgrade procedure on a non-production cluster. Backup etcd, snapshot etcd before upgrading, self-managed clusters. Review deprecation notices, check for removed IPIs and deprecated features in the target version.
What is policy as code, PASI?
Policy as code is the practice of defining organizational policies, security, compliance, operational standards. As machine-readable code that can be version-controlled, tested, and automatically enforced. Why it matters. Consistency. Policies are enforced the same way every time, eliminating human error and interpretation differences. Speed. Automated enforcement removes manual review bottlenecks. Auditability. Policy changes go through code review and Git history, creating a clear trail for auditors. Shift left. Validate compliance in CI before resources are created, not after. Common tools. OPA, Open Policy Agent. General Purpose Policy Engine using Rego language, works with Kubernetes, Terraform, IPIs. Kyverno, Kubernetes native policy engine using YAML, no new language to learn. Sentinel, HashiCorp's policy framework for Terraform Enterprise. Chekhov/TFSec, static analysis for Terraform, CloudFormation, and Kubernetes manifests. Example policies: all S3 buckets must have encryption enabled. Container images must come from the approved registry. Every Kubernetes deployment must have resource limits. Database instances must not be publicly accessible.
How do you debug failed Kubernetes deployments?
A systematic debugging workflow for failed Kubernetes deployments. 1. Check deployment and rollout status.
Kubecontrol rollout status deployment/name.
See if the rollout is stuck.
Kubecontrol get deployment name wide.
Check desired versus available replicas. 2. Inspect pods.
Kubecontrol get pods.
Look for crash loop backoff, image pull backoff, pending, or error states.
Kubecontrol describe pod name.
Shows events, conditions, and reasons for failure, scheduling failures, image pull errors, resource constraints, probe failures. 3. Check logs.
Kubecontrol logs pod.
Application logs add.
Previous.
To see logs from the last crashed container.
Kubecontrol logs pod C container.
If multi-container pod, check each container's logs. 4. Check events.
Kubecontrol get events sort by equals, last timestamp.
Cluster-wide events that show scheduling, pulling, and mounting issues. 5. Common failure patterns. Image pull backoff, wrong image name /tag, registry auth issue, or image doesn't exist. Crash loop backoff, application crashes on startup. Check logs for the error, pending, insufficient resources, CPU/memory. Node affinity mismatch or PVC not bound. Readiness probe failures, app starts but isn't passing health checks. Verify probe endpoint and timing. 6. Rollback if needed.
Kubecontrol rollout undo deployment/name.
Revert to the previous working version while you investigate.
How does eBPF enhance observability in Kubernetes?
eBPF, Extended Berkeley Packet Filter, allows running sandboxed programs directly inside the Linux kernel without modifying kernel source code or loading kernel modules. This gives unprecedented visibility into system behavior with minimal performance overhead. Why eBPF is a game changer for observability. No instrumentation required. Observe application behavior, HTTP requests, DNS queries, TCP connections, without modifying application code or adding sidecars. Kernel-level visibility, see everything. System calls, network packets, file access, process execution. Low overhead, eBPF programs are JIT compiled and run in the kernel, adding negligible latency compared to user space-based monitoring. DevOps use cases. Cilium, eBPF-powered CNI and service mesh that provides network policy enforcement, load balancing, and observability without sidecar proxies. Hubble network observability built on Cilium, showing service-to-service traffic flows, DNS queries, and HTTP metrics. Pixie, auto-instrumented observability for Kubernetes using eBPF, captures full request/response data. Falco, runtime security monitoring using eBPF to detect anomalous system calls. Tetragon, eBPF-based security observability and enforcement. The trend, eBPF is increasingly replacing sidecar-based approaches for both networking and observability in Kubernetes, offering better performance and simpler operations.
How do you handle disaster recovery in Kubernetes?
Disaster recovery, DR, for Kubernetes ensures you can recover workloads and data if a cluster or region fails. Backup strategy. etcd backups, etcd stores all cluster state. Take regular snapshots, automated with a cron job or Velero. Application data. Backup persistent volumes using CSI snapshots or Velero's volume backup feature. GitOps as backup. If all manifests are in Git, Argo CD/Flux. The cluster state is inherently backed up and reproducible, multi-region/multi-cluster. Run workloads across multiple regions so a full region outage doesn't cause total downtime. Use global load balancing, AWS Route 53, GCP Cloud DNS, to route traffic to healthy regions. Replicate databases across regions, Aurora Global Database, Cockroach DB, cross-region PV replication. Recovery procedures. RTO, recovery time objective. How fast you need to recover drives your architecture choices. RPO, recovery point objective. How much data loss is acceptable drives backup frequency. Document and regularly test recovery procedures. An untested DR plan is not a plan. Use Velero for cluster-level backup and restore, namespaces, resources, volumes. Infrastructure recovery. Cluster infrastructure is defined in IIC, Terraform, so recreating a cluster is A.
Terraform applied.
Application state is in Git, GitOps, so redeploying workloads is an Argo CD sync. The combination of IIC plus Git, Ops plus data backups makes full cluster recovery predictable and repeatable.
What is progressive delivery, and how does it differ from traditional deployments?
Progressive delivery is an evolution of continuous delivery that gives teams fine-grained control over how new versions are exposed to users. Using real-time feedback to decide whether to proceed or roll back. Traditional deployment, new version replaces old version all at once, Big Bang release. Binary outcome, it either works or it doesn't, rollback is reactive, you discover problems after all users are affected, progressive delivery. New version is released to users incrementally, with automated checks at each stage. Decisions to advance are based on real metrics, error rate, latency, business KPIs. Rollback is automatic when metrics degrade, techniques. Canary releases route a small % of traffic to the new version, increase gradually. Feature flags enable new features for specific user segments, launch darkly, unleash, flagsmith. A /B testing, compare variants with statistical rigor to measure business impact. Traffic mirroring, dark launches. Send a copy of production traffic to the new version without affecting users. Tools, Argo rollouts flagger, automates canary /blue-green with Istio/Nginx. Launch darkly, feature flags. Key advantage, progressive delivery shifts the deployment risk from hope it works to prove it works with real data before full rollout.
What are Kubernetes operators, and why are they useful?
A Kubernetes operator is a custom controller that extends the Kubernetes API to automate the management of complex, stateful applications. It encodes operational knowledge, how to deploy, scale, backup, upgrade, and recover an application, into software, how operators work. Define a custom resource definition, CRD, that represents the application, for example.
Postgres cluster.
The operator's controller watches for changes to these custom resources. When you create /update a custom resource, the operator takes the necessary actions to reconcile the desired state, create pods, configure replication, set up backups, etc. Why they're useful? Automate day 2 operations, backups, failover, scaling, and upgrades that would otherwise require manual runbooks or on-call intervention. Domain expertise as code. A database operator knows how to safely add a replica, perform a failover, or upgrade a cluster, encoding the expertise of a DBI into software. Self-healing, the operator continuously reconciles, automatically fixing configuration drift or recovering from failures. Consistent management, manage complex applications with the same.
Kube control.
Workflow used for everything else in Kubernetes, popular operators. Cloud-native PG, PostgreSQL, Strimzi, Apache Kafka, Prometheus operator, Prometheus monitoring stack. Cert Manager, TLS Certificate Lifecycle Management, Elastic Cloud on Kubernetes, ECK. Elasticsearch.